Hey, welcome to Ones and Zeros. My name's Ben, and today we are looking at the second video in our STM32 debugging series. In our last video in the series, we took a bit of a look at some of the ways to avoid certain issues with setting up projects and things and copying projects in the Cube IDE. In this video and in the following videos, we're going to start to look at the various tools that you can use to be able to try and track down bugs in your code and some of the different approaches that you can sort of have for your debugging toolbox that are going to make your life much easier. Now, everyone's going to come across bugs. Doesn't matter if you've been programming for 5 minutes or 50 years, you're going to end up with bugs at some point. And having a solid box of tools to be able to help you track down those bugs and find out where they are and what they're doing is the key to be able to keep yourself at least a little bit sane. Although not 100% sure anyone that does programming or electronics is actually completely sane. I think we're all a little bit weird in some way, but that's a good thing. So in this particular video, we're going to look at what I think is an incredibly useful tool, but probably the most simplest tool that you can use for debugging microcontrollers and the STM32s in general, which is the use of LEDs and GPIOs in order to be able to see at a glance what the microcontroller is doing, if certain things have happened or if it's doing what it's meant to be doing. And although it might seem simple, turn an LED on or off, there's certain tricks to it that you can use that will allow you to get a little bit more information than what you might think initially. So some of you might use these sort of techniques already, but there might be something that you've not used before that might make your life that little bit easier as well. So today, what we're going to be using, just as a bit of an example, is the board that we're using for our Discovering STM32 series, which is our STM32F769i Disco. And this is running the code as it was during the last video for that series where we implemented the touch driver. So basically all it's doing at the moment is polling the touch driver, figuring out where we're touching the screen, and then just drawing a box on the screen at where it's detecting our finger. So as we can see there, the update rate's not super high at the moment, which is why it's lagging behind a little, but that allows us to test that's actually working. Now, as I mentioned, what we actually want to be looking at is the ways that we can use LEDs for debugging. Now, on this particular board, it has two user LEDs that we can make use of. It's got a red one and a green one. We can see the green one down there flashing at the moment. The red one is the one that's just to the left of it. And there is a couple of other LEDs on here, but we're not going to be worrying about those in this video. So having two LEDs is a little bit more flexible than just having one, say like we've got on our F411 Discovery board that we've been using for our STM32 Basic series. And although you can do a bit of stuff with one, my typical approach prefers two, which is why we're going to have a look at this particular board. So in this case, what we can see at the moment is through the use of the LEDs, it is telling me straight away, just by seeing that green LED flashing once a second, that the CPU is running and that it's currently executing code the way we want it to. So one of the most useful things I find is having that heartbeat LED flashing on and off at a regular interval, not only because it tells us whether the CPU is running, but if we start to push the CPU too hard and give it too much work to do, or if it's getting bogged down dealing with certain interrupts and things like that, then straight away at a glance we'll be able to see it's not quite flashing as regularly as it would be otherwise. We might see that it might stay on for a shorter period or a longer period, or stay off for a shorter or a longer period, or just seem not as consistent with its flashing on and off. So straight away, just by doing that, we've already got a few bits of information. Is it running? Is it being pushed to a point where it can't keep up? or is it just running normally? And through the use of that one LED, we've got all of that information straight away. Now, we also want it to be able to give us a bit more information as to whether or not there's particular issues that are occurring in the code as well. And there's a couple of different approaches that I like to use for that as well. So if we jump over to the actual code itself, which we can see right here. So this is just our main.cpp for this one. And we can see where we're defining the particular rate that that heartbeat LED is going to tick at. If we go down to our processing loop, down past our initialization stuff, we can see in our processing loop, which starts up the top here, so everything from down there, we can see at the end of that processing loop is where we go about actually flashing that heartbeat LED. So that's that part. However, during all the initialization stuff too, we want to make sure that things are being initialized properly. And we can do things which we can see here as well, where we're printing out, information by serial, and we can do data logging and stuff as well, which we're going to look at in the next debugging video. We can also see, say for example with this, where it's going to initialize the I2C or I2C driver, which it's using for the touchscreen controller, that if that initialization fails, it does print out a message via serial for us, but it's also going to turn on the red LED. And at this point in the initialization, the green LED it's been set up, but it's not turned on. So green LED is off. But this fails, it turns the red LED on. And straight away, at a glance, we can look at the board and go, there's a red LED on, there's nothing happening with the green LED, something's failed during the initialization. So we're starting to develop a bit of a language that the LEDs can use to give us feedback at a glance as soon as we look at the board. And that can start to be really useful. And we'll notice that if we go through where we set up the real-time clock driver, same thing for our random number generator driver, and for various other bits and pieces here as well. So we'll see that in a whole bunch of places during the initialization. So basically, the language that we're developing with the LEDs is telling us that if we've got a red LED on and no green LED, something has failed during initialization. So straight away from that, we know where to start looking in the code. It's something in the initialization section. Now, especially when you start to deal with pointers and things like that, you might get something happening where you cause a memory fault, or you could have situations where there's a bus fault or something like that. And in the case of that, what's going to happen is the CPU is going to jump to one of its fault handlers. So we've got a few here. We've got our hard fault handler, our memory manager handler, bus fault handler, and our usage fault handler. Now, because say if we go to try and access a pointer that's a null pointer or pointing at an invalid memory location, that's a pretty serious issue. We want to make sure that not only does the CPU stop doing what it's doing, but that it lets us know what's happening. So again, we start to add to the particular language that we're creating for our LEDs to speak to us. In this situation, we can see that what we're doing for all of these fault handlers is we're turning on both LEDs for all of them and then chucking it into a while loop so that the CPU gets stuck in that while loop and can't continue to sort of bash around and cause trouble. So again, adding to our language, we know that if it's a red LED on and no green LED, it's an initialization issue. If we look at the board and we see that we've got a red LED and a green LED both on at the same time, then that straight away tells us that it's triggered one of the fault handlers effectively. And I find most commonly that means that at some point I've tried to access a memory location that I shouldn't have, and as a result the CPU has triggered one of the handlers. And especially when we start to deal with C++ code where we've got pointers to classes and things like that, as you might have seen from some of our STM32 basic series or from our Discovering STM32 series, this can be really useful to help narrow that down too. And without even having to get into using serial or the debugger or things like an oscilloscope, anything like that, we can then go through and go, okay, well, this is the bit of code that we've just added. It was working fine before. Let's comment that section of code out and see if that occurs again. And the LEDs will let us know, is there an issue? If we get both LEDs on, we know straight away that that issue is still occurring. It's not where we're looking. If we see that the green LED just keeps flashing and it's happy doing whatever it's doing, then the stuff we've commented out straight away is where our issue is. Now, let's see if we can actually trigger an error with this, just to see if we can show sort of what that will actually do. So let's just create a void pointer, and let's call it temp pointer. We'll go equals null. Actually, let's make it a uint8t pointer. Makes it a bit easier. We won't have to do any typecasting or anything like that. So if I try to put a value in that, so we try to put 8 into the location that the pointer is pointing at, in this case null, and we pop that onto the board, hopefully we will trigger a fault and see the particular behavior that I'm describing. So just copying it across to the board now. Let's switch over to that one. Okay, hasn't quite caused that error for us that we wanted. Be the one time I'm actually trying to get it to misbehave that it doesn't want to. So let's jump back over to our code. Wonder if I can guess off the top of my head an actual memory location that it's not going to like us accessing. Let's just try that. Could pull up the documentation and actually see what's located at which memory addresses, but what's the error we're getting with that? Right. See if that wants to behave for us. Still getting an error with that. Maybe if we can just typecast that. And to give us a bit more of a chance of actually getting this to misbehave, let's pull up our, where's our SDRAM driver? FMC. Let's grab that address there. I think if we change that C to a D, we should get... Still doesn't want to compile. Right. which way will we do this? There we go. That's going to let us do something that we shouldn't be doing there, just by doing it that way. Hopefully we get the result that we're looking for. Again, it's funny that we're having trouble getting it to misbehave. So it's just popping the code over there now, and we see straight away what we were looking for. So we can see it has given us both LEDs, let us know that we've just tried to access an area of memory that we shouldn't. So again, just by looking at the board straight away, we can see that's what it's done. So like I said, bit of an example of how you can actually develop a bit of a language with the LEDs in order to get them to provide you with more information than just is the LED on or off. You can actually start to get it to literally point you at what's going on with the code and where in the code you might have a particular issue. Now, if you're dealing with a board where you've got only one LED, or if two LEDs is not enough to be able to give you some of the information that you might be looking for, you can always go through and add more. And I find the simplest approach for that, another really useful tool for debugging, is this guy right here, which is basically just a blue LED, just connected to a couple of wires so that we can hook that up to microcontroller. And hidden inside the heat shrink there is just a resistor, just to do current limiting so that we don't try and draw too much current from the GPIO pins or burn out the LED. So this can be a really useful tool. And say, for example, with this board, even though we've got two LEDs that we can use for the debugging process, when I start to do the next couple of videos in the Discovering STM32 series, where we start to look at working with the flash memory and the SD card and things like that, it might be useful during some of the testing to actually set up an LED just to briefly flash for say 200 or 300 milliseconds anytime we read or write to the flash memory or the SD card, for example. So that way, at a glance, I can see what the activity is of it accessing those particular storage. Similar to what you'd get with a hard drive LED on an old school computer, for example. But something that don't see quite as much on computers these days, especially with SSDs and stuff like that. But what I do highly recommend is that once you develop a bit of a language for the way you're going to get the LEDs to signal things to you, keep it consistent. So that way you can tell at a glance straight away what's going on. Don't go mixing up the particular language that you're using for the LEDs across the course of a project, and try and keep it consistent across all of your projects, especially if they're projects that you're just doing for yourself, for example, because that way you'll learn that muscle memory or in your mind of what that particular thing means. And again, using the LEDs to me is all about having that information at a glance. So I don't have to worry about getting into the debugger or pulling up a serial terminal or getting out the oscilloscope or anything like that for certain issues, simply because the LEDs are capable of providing a decent bit of information if you use them wisely. So that's kind of what I wanted to cover for this video. I hope you found it interesting. Like I said, in the next one, we're going to start to look at using serial for data logging and for getting additional bits of information back from the microcontroller as far as how different things are running, which can also be an incredibly useful tool. Beyond that, we will be taking a bit of a look at the CubeIDE debugger and how we can use that with various different STM32 devices in order to get even more information. And that is something that is incredibly powerful in the sense that we can see inside the chip and its peripherals and see what's actually going on. So that's really useful in situations where we may want to step through the code and set breakpoints and things like that, or even go in and see how variables are changing over time, or whether we're setting up particular registers for one of the hardware peripherals, things like that. So again, another useful tool in the toolbox to have. We will also go through and touch on things like multimeters and oscilloscopes. And we'll take a bit of a look at the Siglent scope that you've possibly seen on some of my other videos, and how we can use that to debug various things as well. So a bunch of different approaches we can use there, especially because this scope does also do digital decode for things like UART, I2C, SPI, and that sort of stuff that you may have also seen in previous videos. So we'll go through and have a look at kind of how that works as well as a tool. And through doing that, you'll end up with a whole bunch of tools in your debugging toolbox, because the more you have, the easier it is to try and find a particular issue. Like if you're building a house, you're not going to use a screwdriver to hammer in a nail, or you can, and similar to using one debugging tool in a situation where another one might be better suited. But if you use a hammer to hammer in a nail, it's going to do a better job, it's going to work quicker, you're going to end up less frustrated. And as anyone that's done a bit of programming understands, debugging can be a bit frustrating. If you can use your system of debugging tools in a way that allows you to avoid as much of that frustration as possible, then you get that out of the road and you get to actually enjoy more of what you're doing with the programming and with the hardware development and things like that, which is highly recommended. Going on that as well, I mean, one of the main psychological things with debugging is to learn how to stay calm, because bugs happen. And one of the things that I really enjoy about doing these videos is, as you saw, just trying to get it to misbehave. There's no point getting frustrated about that. If I got frustrated about that, it would make the videos much less enjoyable for you guys, I would think. So yeah, that's kind of the philosophy that I like to take with that. If you liked the video, would love it if you liked, and hit subscribe if you haven't subscribed as yet. Thank you to all of the people that have, especially a lot of the more recent ones. We're nearly up to 200 subscribers as of the point of making this video, which is awesome. And if you do want to help support the channel, then we do also have a Patreon down in the corner there somewhere. And there's various benefits for patrons depending on which level. All of the patrons, of course, do get access to our private Discord server and things like that, where you can ask me questions or give me feedback, chat with other patrons about the particular projects they're working on, stuff like that as well. So the aim there is to make a nice community for people to be able to share cool ideas and stuff like that. And of course, we do have our very first patron who has just recently joined, which is Craig. So thank you very much, Craig. It's awesome to see that you're helping to support the channel. I'm very grateful for that. And yeah, next video in the series, like I said, we'll be looking at using Serial for debugging. Hope you have a wonderful day or night, morning, evening, whatever it is where you are watching this in your part of the world. And thank you very much for watching.